we are now going to question 2A of section 20, right? We are continuing with quiz 3, but now question 2A of section 20. So the question is, name the 3 invariant reactions that take place in the iron-iron carbide phase diagram. Write the equations for any 2 of them, right? So you remember that the iron-iron carbide phase diagram means the steel phase diagram, and there are 3 invariant reactions. So in terms of names, write the names of all the 3, but for the equation, right, for the equation you write any 2 of them, and I will accept it. If you have written all 3, then it is great. So this is it, right? This is it. At the very top of the diagram, there is peritectic reaction which happens at 1495 Celsius. So the liquid and the delta phase, right? Delta phase change into gamma phase, right? These percentages, if you don't remember, then it's okay. But the temperature should be roughly there. You should at least write about 1500 Celsius or plus 1400. If you are 1490 or 1495, it is very good. But liquid plus delta changes to gamma at a very high temperature. This is peritectic. Then the eutectic for a steel or iron-iron carbide diagram. Eutectic always means that liquid changes to 2 solids. So liquid changes to gamma austenite and Fe3C, which is iron carbide. And this is now important because eutectic composition is important. Peritectic, if you don't remember, it's okay, but eutectic is 4.3% carbon, 4.3% carbon, and it is roughly 1150 Celsius. So these are important. This percentage or this percentage is automatic. This percentage, iron carbide, is always 6.67%. So this you should write if you know. This, if you remember that it is about 2%, it would be very good. Otherwise, I'll still take it as correct. Eutectoid is again very, very critical because we have done so many examples on eutectoid. So one solid changes into 2 solids. One solid changes into 2 solids, that is eutectoid. So the gamma austenite changes into alpha ferrite and cementite. And this is important. You should remember that eutectoid happens at 0.8% carbon, right? This, if you remember or you not remember, is okay, that the alpha in the eutectoid is 0.02%. But if you don't remember it, I'll still take it as right. But this iron carbide is always 6.67%. So if you write only peritectic, eutectic and eutectoid in terms of names, you are okay. If you don't write the peritectic reaction, write only eutectic and eutectoid, you are okay, or any 2 of them, right? So this was question 2A of section 20. This is important because you see, steel is the biggest single alloy used in the whole world of engineering. And iron-iron carbide diagram is the phase diagram of a steel. So whenever you are in any interview or you are talking to anybody and you say that I know the phase diagram of a steel, but I don't know the 3 invariant reactions, then it is bad. So these names, peritectic, eutectic and eutectoid, especially eutectic and eutectoid with some details you should have in your mind. Let's go to the second part of the question, question 2B of section 20. A 0.25% carbon hypo-eutectoid plain carbon steel is slowly cooled from 950 Celsius to a temperature just below 723. Calculate mass fractions of pro-eutectoid ferrite, eutectoid ferrite and eutectoid cementite in the steel. The diagram will of course have to be given to you, right? So this is a steel phase diagram or the iron-iron carbide phase diagram. When they say hypo-eutectoid, right? So this is the eutectoid composition, 0.8%. Any composition less than this, right? From 0 until 0.8 is hypoeutectoid. But here 0.25% is already given to you. So you will draw a vertical line at 0.25. You are roughly at this temperature, 950 and so on. And then you cool to almost 723 or just below it. So I have already done that here for you. We have enlarged the diagram and we have drawn a line, we have drawn a vertical line roughly here. So you are going from 925 to just below 723. So your horizontal thermal line is 723, right? Just below 723, just below 723. And this means that on the left it will cut alpha at 0.02%. On the right it will cut iron carbide at 6.67. So your tie line, when you are just below 723, then in the middle you have the given percentage, 0.25% carbon. On the left you have 0.02% carbon for alpha. On the right you have 6.67% carbon for iron carbide. So this is it, and once you draw the tie line, then everything is there. So what was the question, right? You have to find the eutectoid compositions, right? You have to find the eutectoid compositions. Now the thing is, if you remember, right, that when you are above this temperature, just above this line, and you draw a tie line, then alpha will still be 0.02%, but here you will have gamma. You will have gamma at 0.8. So just above 723 plus delta T, your tie line reads left alpha 0.02, middle 0.25% carbon, right gamma 0.8% carbon, right? Because from here you will find pro-eutectoid alpha, pro-eutectoid, right, and so on. So whatever gamma was there changes into alpha first. So whatever alpha is forming here is pro-eutectoid alpha, and at this line just above it, whatever alpha you find there is the amount of pro-eutectoid alpha. As soon as you come to below this temperature, then you find the total alpha, right? And finally total minus pro-eutectoid will be the amount of eutectoid. As far as the other part, the cementite is concerned, there is no cementite formed here. So whatever cementite you are finding just below 723, you call it total cementite, or you call it eutectoid cementite, or you call it just cementite. They are all the same. Alpha is pro-eutectoid and total and eutectoid, right? But cementite is not formed above this temperature, it is formed only below this temperature. Therefore all of that cementite you can call only cementite, or you can call it total cementite, or you can call it eutectoid cementite. These will be the same. So once you, as I always repeat in the class every time, any question on the phase diagram, there is a vertical line, there is a horizontal line, draw the tie line. As soon as the tie line is there, all your answers. What are the phases present? What are the compositions of the phases? What are the mass fractions of the phases? Everything is there. So we are showing the full solution here. The first part was give the mass fraction of the pro-eutectoid ferrite. So this is the temperature plus delta T, right? So 0.8 minus 0.25, 0.8 minus 0.02, the percentage is there, right? Above. And then below, just below the temperature line, total cementite or cementite, 0.25 minus 0.02 and so on. Total ferrite, right? So above, right, the given temperature plus delta T is this part, which is pro-eutectoid ferrite. Only ferrite is formed there. But below, just below the temperature, and we are showing one part of the tie line, you can do the other part yourself. So this is total cementite and total ferrite. Now as I said, this total cementite, call it only cementite or total cementite or eutectoid cementite. It is the same answer. But total ferrite minus pro-eutectoid is the eutectoid ferrite. So eutectoid ferrite is total minus pro-eutectoid. So these are the two answers of the second part, right? So this is a very standard question. This is not a trick question. You have done these type of things many times earlier, and that is why, I mean, if you see the results of quiz 3, most of you got pretty good marks and so on. So those few of you who did not get good marks should really look at themselves and see that, you see, this is a very standard question, And many examples like this are done in chapter 8 on phase diagrams and chapter 9 on engineering alloys. And if you revise even the problems which are solved examples in the class, then you should get it 100% right? So here you are. This finishes quiz 3. Now we will move to quiz 4, right? So now we will move to quiz 4, and as always, in the beginning we will go to question 1, which is the multiple choice and true false, and we will give you some examples. So let us start. Dash has a BCC structure and a coordination number of 8. Tellurium, bromide, zinc blend, magnesium oxide, none of these. So now because there are only 3 structures that we have done. We have done the cesium chloride structure, the sodium chloride structure, and the zinc blend structure. And there are lots and lots of others which are there in the chapter, but we have left them, that this introduction is good enough for you. Later on, if you end up in a ceramics industry, then you can read the other things, right? So because there are only 3 structures, cesium chloride, sodium chloride, and that, so therefore you should know that out of that list, something which has a BCC structure and a coordination number of 8, tellurium bromide is the correct answer for this one. Second question, number of anions surrounding a cation in an ionic ceramic is called what? This is a very, very simple thing. Of course, it is called the coordination number, not the atomic number, not the Avogadro number, not the Boltzmann number. If somebody has finished the chapter on ceramics and he does not know what is a coordination number, then it is really bad, right? So this hopefully everybody would have gotten right. Next question, in the dash unit cell, anions occupy FCC atom lattice sites and cations occupy the interstitial sites. So this is only one of them. As I just said, cesium chloride, sodium chloride, and zinc blend. So there is only one of them where the structure is basically FCC, and in the gaps in between them, interstitial in between them, the other atoms are there. So the correct answer is not tellurium, not cesium, it is sodium chloride, your common salt. So, right, so this was the only example, right, of the structure of a ceramic where it is FCC type with one type of ions in all FCC places and the other type of ions in all intermediate interstitial places. Next one, ceramics have high chemical stability and high melting temperature. This is of course true, right? If anybody writes false here, then I am really surprised. In ceramics, bonding is mostly covalent and some ionic, right? So this is definitely false because it is a combination of ionic and covalent. But mostly in most of the ceramics, mostly it is ionic. Mostly it is ionic with some covalent there, right? Because of the electronegativity differences and so on and so forth, right? So this should definitely be the thing. If the anion touches the cation in a ceramic, then the arrangement is unstable. Definitely false. If you remember the triangular structures and so on that we showed you, right? Then if there is a gap between the smaller and the larger atoms, then when you try to deform it, it will easily deform. But when the smaller one touches the larger one, then there is no space in between. So when you try to deform, deformation will be very tough and difficult. Therefore, it is true, right? The arrangement is stable normally. When it says unstable, then it is a false statement here. So we finish here and we will continue in the future, inshallah.